Find the points on a curve where the tangent line is horizontal. The first thing we need to realize is that a horizontal tangent line has a slope of 0. And slope, of course, is a derivative. So what we're really being asked to do is find the places where the derivative is equal to 0. So our strategy would be to find the derivative and set it equal to 0 and then solve the resulting equation. And that will give us the x-coordinates of the points where the tangent line is horizontal. So our derivative is 4x cubed minus 12x, using the power rule and the sum and difference rules. And solving 4x cubed minus 12x equals 0 gives us x values of 0 and plus or minus the square root of 3. And if you're not sure how that got solved, we factor out a 4x. That gives us x squared minus 3. Set each factor equal to 0. 4x equal to 0 is what gives you your 0 solution, and x squared minus 3, when we solve it, gives us plus or minus square root of 3 as our solution. And there's what the graph looks like. The curve is the blue line, and then here are the points we found where the tangents were horizontal. And of course, if we know 0 square root of 3 and negative square root of 3, we simply plug those into the original function to get the y values of 4, negative 5, and negative 5 that go with those x values into the original equation, because we want points that are on the blue curve. The equation of motion of a particle is given here, and they ask us to find the acceleration as a function of time. And we've discussed previously that acceleration would be the second derivative of position. So if s is given here, then the derivative of s would be the velocity, which would be 6t squared minus 10t plus 3. The acceleration at time t would be the derivative of velocity, which would be the second derivative of the position function. And that would be 12t minus 10. So that would be the answer to this. The acceleration as a function of time would be acceleration is equal to 12t minus 10. And then, of course, the second part is easy. Once we have the acceleration function, after 2 seconds, we would simply say a of 2 is equal to 12 times 2 minus 10. 24 minus 10 would be 14, would be our acceleration. Let's see, it's centimeters per second, so centimeters per second would be the units on our acceleration. Now let's look at the value e. We have said previously that e is an irrational number equal to approximately 2.71828, and we encountered this before when we were looking at tangent lines and exponential functions. And it so happens that we can define the number e to be the limit as h approaches 0 of e to the h minus 1 over h to equal 1. So e is that number that makes this limit come out to be exactly 1, or that makes the slope of the tangent line of that exponential function equal to 1. Geometrically, if you recall, that means that of all the possible exponential functions y equal a to the x, the function f of x equal e to the x is the one whose tangent line at the point 0, 1 has the slope of exactly 1. So its derivative at 0 is exactly 1. And the derivative of the natural exponential function is actually just e to the x. The derivative of e to the x is e to the x. It has the property that is its own derivative. So the geometrical significance of that fact is the slope of the tangent line to the curve y equal e to the x is equal to the y-coordinate of that point. So the slope of x e to the x is equal to e to the x. If f of x equals e to the x minus x, find the first derivative and the second derivative. And then compare the graphs of f and f prime. So if we find the first derivative, we can use that this is a difference of two functions, so we can look at the derivative of e to the x individually, and we just learned that it is its own derivative. And the derivative of x is going to be minus 1. So the first derivative is e to the x minus 1. The second derivative we get by differentiating the first derivative, so we're looking at this function. And the derivative of e to the x is simply e to the x, and the derivative of the constant 1 is 0. So the second derivative would be e to the x. And here's what the graphs look like. Here's the function f, and here's its derivative in blue. And notice that f has a horizontal tangent when x equals 0, and that corresponds to the fact that the derivative at 0 is equal to 0. Notice that for x is greater than 0, the derivative is positive and f is increasing. And notice also that for x is greater than 0, the derivative is positive and f is increasing. And when x is less than 0, the derivative is negative and f is decreasing. At what point on the curve y equal e to the x is the tangent line parallel to the line y equal 2x? If a line is parallel to another line, their slopes are equal. They're asking me to find the point on the curve y equal e to the x where the tangent has a slope of 2. So they're asking me where is the derivative y prime equal to 2. So the question is, when is e to the x, because y is equal to e to the x, so when is the derivative of e to the x equal to 2? Well, y prime is equal to e to the x because e to the x is its own derivative, so they're asking where is e to the x equal to 2. So I would take the natural log of both sides to solve this equation. And the natural log of e to the x is simply x, so the solution to this equation would be when x is equal to the natural log of 2. Thus the required point would be the natural log of 2, be right here, and here's my line y equal to the x, and here is the line that goes through this point and is parallel to the line they gave me.